Alright, hello everyone. So last time what we did is, well, we saw what is resistance, right? So resistance was basically the our push that we have on each charge or each unit of charge, which is formally our voltage divided by, for that push, how much movement are we getting? Okay, how much does the charge move, which is formula current, right? So resistance was our voltage divided by our current. What I want to do in this video is look at the factors that affect resistance, specifically the resistance of metals, alright? And the first factor that I'm going to talk about, the first factor that we have here is, um, I'll choose a red color actually for this, because whenever I think about temperature, kind of think about things getting hot, so red seems like a good color. So temperature, right? So for that, let's first draw a piece of metal. Let's first draw a piece of metal. So see, we have our metal. Okay, this is a piece of metal, and well, for our purposes in this lecture, we're gonna assume that this metal has a uniform cross section. Okay, uh, you know, this is a straight piece of metal. This is a straight piece of metal which has a uniform cross section. That would make things easy for us. The straight part isn't that important, but the uniform cross section is important. So, all right. So let's do something. Let's zoom in. Okay, let's zoom in at a portion of this metal. So let's see, if we zoom in here, see, if we zoom in here, what do we get? We saw this before in the last video, where we saw how how does a metal conduct electricity, how does electricity flow. Basically, how do the electrons flow here. So in this metal lattice, you have you have your ions. Okay, so you have your metal ions. Okay, um, you have your metal ions. Mm, oops, oops. So let's see. All right. And you have your electrons, right? You have these ions are mostly fixed. They just vibrate in their positions, and the ones that are free, that do actually conduct the electricity, or the charges that are actually allowed to flow, those are your free electrons. Okay. And by the way, I could put charges on the ions, but let's not clutter the diagram. Okay. uh, they are ions, in fact. Okay, they are charged, they are positively charged, but let's not clutter the diagram. Anyways, so we have these electrons, and the electrons are the ones that actually move, right? The electrons are the ones that actually move. Like the electrons, let's see, if let's see, wait, if my voltage source is like this, so my voltage is being applied in this direction. uh, so yeah, the electrons actually flow from the negative end to the positive end. Our conventional current, if someone told you what is the current direction, they're not telling you what current. We just have to assume that's our standard conventional current. So this is the direction that you would show. Okay, if someone asked you, okay, so what's the direction of the current, right? So that's just become a convention for us, for all of electricity. But however, the electrons, since we are looking at it from, at a microscopic, and specifically, we do want to know where the electrons move, or we're seeing that. We'll show the movement of the electrons. Okay, the electrons do in fact move from the negative end to the positive end. It's from the right to the left, so we are right. We are correct in drawing this direction. So, anyways, that's for the previous. That was the previous video. We'll not talk too much about it. So, uh, yeah. So the electrons are basically gonna move in general from the from this end to this end. So this is what happens in the metal. All right. Now I wanna see. So if I increase the temperature, what happens? What happens? Well, uh, the ions. Okay, so as I said, the ions do vibrate in their positions. Okay, so like the ions, like this ion is vibrating here a bit, there a bit, sometimes up and down, a bit of left and right too. So anyway, so they're basically vibrating in their positions. What happens if you increase the temperature? Well, naturally, we know our kinetic theory. These ions are gonna vibrate more, right? They're gonna vibrate more. Okay, they're gonna vibrate more. Okay, they're gonna oscillate more, you could say. So these are vibrating a lot more. Okay, the ions. And what happens if what would happen if they do vibrate more? Well, even before, as I said, in the last video too, and you can see it here too, the electrons, it's not like they're just going to go smoothly from the right to the left. They are going to bump into the ions. Okay, they are going to bump into the ions and change their direction, and but eventually they'll reach the left end, right? Okay, if the ions vibrate even more, well, the electrons are going to bump into them even more, right? So suppose say this electron, since these ions are bumping more, so it's going to wait, not that color. Let's pick blue. Okay, so let's see if this electron. See, because of how much these ions are vibrating, suppose that this gets bumped into this ion, and then into this one also, then into this one also. So it's going to bump a lot more. Okay, bump a lot more into the ions. Okay, the electrons, and that's why they're going to take more time. Okay, to reach the left end, or it's going to take, it's harder for them. Okay, it's much harder for them to reach the left end, right? An analogy that comes to mind is, I don't specifically remember the name of this game, but if any of you have played this, I think it might be a bit old school now. But so you have this block, okay, and you have this I don't know what you call it, some paddle or anyways. So you have this bar at a horizontal bar at the bottom, and you have these bricks, or yeah, you have these bricks, marbles, whatever you want to call them, on top. Okay, and basically you have a ball here. I'll change color. Basically you have a ball here. Okay, and this ball is going to move, it's going to move up after hitting this pad. Okay, and it's gonna break one of the bricks, or whatever you want to call them, and it's gonna come down. What do you need to do? What the goal of this game is, you need to move this, okay, pad left and right, so so that you keep the ball up, okay, every time. You don't let it fall. If it falls below this, okay, it's gonna be game over. Anyways, so you can think of it like this. You can think of the electron like this ball, okay, and your ions like this bar that you have. Your ions, you can let me do it in the same color. The electron, the electron is the same. There it's green, and this is your ion. Okay, this is your ion. So the thing is, if you're able to move this quicker, okay, so if you're a better player, okay, and are able to move this quicker, what happens? You can keep this ball afloat much more easily, right? You can you can stop it more easily, bump into it more easily, and you wouldn't get a game over. Okay, you're getting a high score. Think of it like this. Okay, so the the if the ions do move fast, okay, do vibrate faster, the electrons would get stopped a lot more. Okay, the current would get impeded a lot more. So it's basically your current, the electron flow, is getting resisted more, right? It's getting resisted more. That's why naturally, as we see, if my temperature is higher, my resistance increases, right? My resistance increases. My resistance, I'll just write R. My resistance increases. So that should be that should be eh, that anyways, I don't know what word I was searching for. Just one thing, if any of you are curious about the exact mathematical relationship between these two, you can search for temperature coefficient of resistance, but we won't get into that. um, it's I think it's enough just to know that the for now that temperature increases, the resistance increases, and actually vice versa too. Okay, if the temperature, if the temperature decreases, okay, so does your resistance, so does your resistance. You just use the reverse logic. All right, so that's for temperature. That's enough for temperature. Let's move on to our next factor. Okay, let's move on to our next factor, which is okay, so that is the length. Okay, the length, okay, of this piece of metal, of this piece of metal conductor. Okay, so and for this, let's see what do we have here. All right, so let's draw this. Okay, let's draw this. So we have, well, yeah, this is fine. Okay, so before going to that, let's look at an analogy. I think this analogy is actually pretty neat. Let's see. So suppose say we have a racetrack. Okay, suppose say we have a racetrack. Okay, all right, so suppose say we have a racetrack. Okay, and here and here you have, at the beginning you have a bunch of race cars. Okay, so you have your race cars just waiting for the signal to start. Okay, and the race happens, and they need to cross, this distance to get to the finish line, right? So this is the finish line, so they need to get to the finish line by crossing this distance, or this length, you could say, this length. Okay, all right. Now what happens if instead of this this small track, this length of track, what happens if I had a, what happens if I had a longer track? So actually, let's see. So what happens if I had a longer track? Okay, and I'll erase this bit right here. um, this is no longer the finish line. Okay, this is no longer the finish line. So now, okay, so now my finish line is here. My oops, that's didn't change the color at all. Okay, so my finish line, it's not no longer here, it's actually here. Okay, and yeah, the length is more. Okay, so we have a greater length here, so of the track. Now what happens? Our race cars, they're gonna take more time to reach the reach the end, right? Reach the finishing line. Okay, and it's basically gonna be harder for them to complete the race, right? And you might, sometimes it happens in those professional racing tournaments, that some cars don't actually make it to the finish line. So you might think of it that way too, that some cars here, maybe they'll just get exhausted, or something else happens, they might not make it to the finish line if it's really long. All right, so similar thing happens with the wire. Okay, so with our piece of metal. So if it was something like this, okay, and this is one piece of metal, and you have you have one with the same, so let's say it has the same cross sectional area. Okay, but the length is just more. Okay, the length is just more here, okay. This is, the electrons are actually gonna have a harder time reaching from one end of the metal to the other, as opposed to if your bar of metal was shorter, right? So the electrons are gonna have a harder time to reach the end, or the current flow, or the charge flow is being resisted more, right? So uh, we got our second conclusion, right? We got our second conclusion, that if our length increases, similar to our temperature, similar to the effect of temperature, our resistance increases too. And vice versa. If your length, the length of the this piece of metal decreases, if it's smaller, your resistance would be smaller. And actually actually there's we can actually um, put a very write a very simple relationship for them. It is indeed true that the resistance is proportional to the length, provided your temperature and cross section area anyways, the other stuff is constant. uh, your resistance is going to be proportional to the length, okay, of the piece of metal. And I won't prove it here. You can actually prove it yourself. You can watch my series resistance video, and I'll give you a hint on how to prove this. So suppose say you have you know this this piece of metal, okay, this piece of metal, this has a length of L, some area, cross section area A, and a resistance of R, okay. And then suppose say you have another piece of metal, okay, which is a length of 2L. You need to keep the other things same, so it's the same cross section area. And this longer piece of metal is actually equivalent to if you had two whoops two pieces of metal. I'll use that blue color. If you had two pieces of like the previous one, like the previous shorter piece of metal, if you have two of them, okay, of length L in series, okay, in series, okay. And what happens if they're in series? So if previously it was a resistance of R, if you just had the length of L, and now two identical pieces of them and they're in series, so now you're gonna have uh, these resistance are going to add, so you're going to get 2R, right? So as you can see, length doubled, so this was equivalent to this one, right, this one. So length doubled and your resistance doubled, so it does show the proportionality relationship. Well, that was actually more than just a hint, but anyways, yeah, I think it should be enough to at least convince you that the resistance is indeed proportional to the length. All right. The last one, what I want to talk about is actually your cross sectional area. Okay, so your cross section area. Okay, and for this one, we're actually going to use the same analogy as before. Okay, so suppose say you have your racetrack again. Suppose say you have your racetrack again. Okay, let's suppose say you have your racetrack again. Okay, so again you have your cards. You have your cards. I'll just draw it. I'll just draw them like this. Okay. Let's see. What now? Let's try to imagine what would happen. Let's see. Let's try to imagine what would happen if I had a wider racetrack. So instead of just this much, instead of my starting line being the just this wide, or the passage being just this wide, what if I make it wider? What if I make it wider? The same length, okay. I'll keep the length the same. As you can see, I shouldn't have erased that much, anyways. So what happens now? Well, interestingly, before what did you see? What did you see? We had our cars bunched up like this, okay, bunched up like this, and even in the race they're gonna, it's not like they can break away from the track, so they're gonna have to pass through like this. They might bump into each other, and there's just less space and leeway for them to move, right, at least sideways, right? So but now things are a bit different. They can be spaced apart. They can be, they can start off like this. They have a bit more leeway to move around, even in the during the race. Don't have to worry too much about bumping into someone else. So it's just easier, right? It's just easier for them to complete the race. Okay, it's just easier for them to complete the race. Less chances of any mishaps, right? So a similar situation here, okay, with your piece of wire. So you have let's see, you have your piece of you have your piece of metal. Sorry, I keep saying wire, but anyways, it's not technically wrong to call it a wire, but anyway, so you have your piece of metal. Let's say this one has an area of A, okay, length of L. Well, so if you have a wider, okay, some another piece of metal. It has same length but a wider area. Okay, has a wider area here, right? What happens is the electrons, okay, the electrons in it, um, they're actually, they're actually gonna uh, they have more of a passage. Okay, you can see the, the passage for them. Okay, the passage for them, it's wider, right? They have a wider passage. Okay, that's why it's easier for them to reach the end. Okay, that's why it's easier to go from one end to the other. So your current or your electron flow is being resisted less, right? So your resistance is actually lower. Okay, your area increased, right? Your area, here your area increased here. Okay, and so your resistance actually decreased. So let's write that down. Let's write that down. So I'll use this color. So your area has increased and your resistance has decreased. And this is, you can also we can also write very specific simple relationship for this. The resistance actually inversely proportional to the area. And again, like the previous one, you can actually prove it. Okay, I won't go into this much again. That really wasn't a hint as much as it was a full proof. But again, I'll just give you a hint. Do a similar thing. Okay, so you have your conductor, sorry, your piece of metal, area A, length L. Keep the length the same, double the area. Okay, keep the length the same, double the area this time. Okay, so it's 2A L, and this is actually equivalent to if you had this piece, two of these pieces in parallel. Okay, instead of in series, this would be equivalent to if you had two of this piece in parallel. And as you know, and your resistance, as you'll see, it's actually going to get halved. It's going to be R by 2, so proves the inverse relationship. Anyways, so we this should be enough to satisfy you that your resistance is actually inversely proportional to the area, to the cross sectional area. And so we are done. Just as a summary, the resistance of a piece of metal is affected by a bunch of factors. One is temperature. If your temperature is higher, your electrons are going to bump into the ions, which do move, do vibrate more. Your resistance is going to increase, and vice versa. Your length increases, electrons have a harder time reaching the end, your resistance increases, and vice versa. If your cross-sectional area increases, electrons have an easier time moving around and reaching the end, your resistance decreases, and also vice versa. In the next video, we're gonna actually investigate a new quantity or property based on using our these two relationships that we derived. Okay, so see you in the next video, and study smart.